Good evening. My name is Elizabeth Owens, and I'm a junior studying aerospace engineering and legal history. My research is under Dr. Jordan Larson in the Laboratory for Autonomy, GNC, and Estimation Research, which contributes to UA's Remote Sensing Center. My project is titled Adapting Multi-Sensor Fusion for sUAS Landing Operations. The motivation for this work comes from our lab's approach to GPS-denied environment navigation, with this project focusing on a small uncrewed aircraft system, which is essentially a research drone that weighs about 55 pounds. These aircraft are versatile and flexible and are easy to test with, but because of their small size, they're very susceptible to wind, terrain, or sensor failure and noise as they start to land. Previously, our lab has developed a data set for ground vehicle navigation in GPS-denied environments. This data set fused optical cameras, thermal cameras, inertial sensors, and a stereothermal LiDAR, scanning mirror LiDAR, for both visual-based navigation and terrain-based navigation. One reason that data set was extremely beneficial was because researchers were able to test their fusion algorithms in environments that aren't easily recreated in the real world. So for example, really bright lights or really crowded streets. So now our idea is to extend that same philosophy to aerial vehicles. But drones have a really unique set of challenges. The dynamics are much faster, the environments are variable, and the sensors have a lot of unpredictability, especially near the ground. So we're taking the logic of this past data set for ground vehicles and adapting it to a much more complex, bigger issue. As I mentioned, landing can be deceptively difficult for small drones. The last 10 to 15 feet of descent pose many challenges, the biggest one being that they can really exaggerate all of the weaknesses of sensors. So some sensors might be blinded by lighting changes or drift, or maybe they just don't adapt fast enough for fast motion. But the good news is that each sensor sees the world in a little bit of a different way. So in a scenario where one sensor might fail, the odds are that another one is still reliable and still alive. That's the core idea behind redundant sensing, or using more than one sensor for the same thing to ensure that the aircraft always has an estimate of both its altitude and its orientation without relying on a single point of failure. The platform that we're using is called QUESO. It's an autonomy research drone that was developed in our lab, and its size allows us to house and integrate our entire sensor suite, which, as you notice, is very similar to the sensors that were used in the ground vehicle dataset. So 2 optical cameras, 2 infrared cameras, a radar altimeter, an IMU, which is just an inertial sensor that's used in drones, as well as a GNSS receiver and an FPGA, which will just go on the drone so that we can help sense the measurements of the sensors. Using a variation of sensors can make it so we can test different landing environments and situations and determine which sensors will fail and which will succeed. For example, GNSS, or Global Navigation Satellite System, give a really solid estimate of position as far as longitude and latitude, but they don't directly measure the distance to the ground, which is the distance that we really care about when it comes to landing to avoid crashes or damage. Also, as the drone actually moves closer to the ground, GNSS becomes more unreliable because urban canyons or tree coverage, shadows, as well as multipath, which is the effect you see on the screen with the sensors bouncing off of buildings or tall objects, really affect the accuracy of the GNSS sensors. Cameras are a good alternative, but only when they have a clear view of the landing site. So in cluttered environments, like the past slide, the camera might see houses, fences, shadows, anything but the landing site directly beneath it. In flat open fields, like the one seen on the screen, vision can still fail due to a lack of texture. So on grass, sand, or concrete, anything uniform, the camera doesn't have anything to lock onto and has a really hard time detecting its distance to the ground. Similarly to GNSS, cameras can also be more unreliable as they get closer to the ground. This is because drones tend to kick up clouds of dust or debris as they land, which completely clouds the camera view and makes it pretty much unusable as the drone lands. In turn, barometers actually measure the altitude of a drone based off of surrounding air pressure, which, as we know, is extremely affected by wind, weather, or even downwash from the propellers on the vehicle itself. So what happens there is you get a lot of drift with the barometer readings, even when the drone's not actually moving. So you can see that effect here. The barometer reading has spiked up, even though the drone's altitude hasn't actually changed, just because of the air pressure difference due to the windmills moving. Over a long descent, this tends to add up, making barometer a really poor choice for a singular sensor without extra help. A radar altimeter from all of our sensors is the only one that actually does directly measure the distance to the ground. So it does this by sending pulses downward and then measuring the distance that it returns back to the drone. Over smooth, flat surfaces like pavement, radars can be extremely accurate, up to like a few centimeters, but this ideal scenario rarely holds, as most outdoor environments have uneven slopes or grounds where the beams start to scatter. And that's where we see those sudden spikes or dropouts right before touchdown, which, as we mentioned, are really poor moments to have uncertainty. So across all of our sensors, we're seeing this pattern. There's certain situations where they might fail or become unusable, but they all fail in different ways and in different situations. So if we can combine them, we should have an estimate for almost any landing scenario. This is where sensor fusion comes in. A Kalman filter combines predictions and measurements. So first, it takes a prediction from physics, where the drone should be going based off of its inertial sensors and its acceleration. Then it compares that prediction to the readings from all of our sensors, and if a sensor suddenly starts to disagree with the physics prediction, like a GNSS jump or a radar spike, the Kalman filter automatically can give less weight to that particular sensor. So our general fusion architecture takes all of our sensors, including both of our two types of cameras, feeds it into the Kalman filter, and we should get out a landing estimate that's accurate even when individual sensors start to fail or degrade. Moving forward, we can start to put these sensors through simulation in similar scenarios like the ones I showed you to develop a data set that's similar in structure to the ground vehicle data set, and test the fusion algorithms in situations where we know that at least one of our sensors will fail so that we can update it. Then we can conduct real flight tests to compare and confirm that data before our long-term goal of a robust landing estimator that can integrate with future flight computers for research autonomy. Thank you so much. I'd love to answer any questions.
So I kind of missed the last point on the fusion. Were you talking about combining the ground and the air vehicle together and using sensors across both?
Sort of. So it's a similar idea of the fusion algorithms. They're using similar sensors, but it's a different situation with the same sensors. So the ground vehicle is in different scenarios as to navigation, but it's the same idea.
It seems like they could collaborate, right? So the aerial vehicle can help upcoming terrain for I'm thinking like even a military context. And then maybe the ground vehicle can give some signal up to help with the altimeter. So I'm just wondering, since they're so similar, you originally spoke of them as two separate kind of projects, but it seems like the fusion of that and the synergy across all those sensors for unique kind of capabilities that they can share would really be powerful.
They're very similar, and it's definitely an extension of the ground vehicle project.
How does your filter decide which sensor to trust when landing?
Yeah, the great thing about the Kalman filter is that it doesn't trust any singular sensor. So I'd like to relate it to like a weighted average when you're thinking of course grades. So depending on how close the measurement is to the real ground truth value, the filter adjusts the weighting of each individual sensor in order to determine the overall average.
There's laser altimeter. You looked at that instead of radar?
There is. I actually did a project last year on using rangefinders, so that was more similar to the lasers.
We have a question from Michael Zangel. Are there any plans to integrate artificial intelligence to develop a more predictive model?
As we work toward more autonomous flight computers in total, I would say that's more similar to artificial intelligence, but it's not AI, it's just autonomy, which are similar but not the same, but sort of.
About like large federations, you have many ground vehicles, many aerial vehicles. Is that kind of like, what there's obviously communication issues, but is there any kind of long-term kind of goal of something like that?
Could you clarify, like, for ground vehicles in particular?
Yeah, I got hundreds of ground vehicles, I got hundreds of drones, and they're all in a federation kind of collaborating. What are some unique things that those sensors could be sharing?
Like communication-wise? I mean, I think it would help mostly in that situation with like air traffic control stuff if you're talking about drones. For ground vehicles, I think that'd be a really interesting thing to explore as we get into like self-driving cars and things like that. So that's a really interesting idea. I hadn't thought of that.